Okay, I decided to separate the complex numbers from the uh, regression line thing. Okay, the least squares idea. One, yeah, and one more comment I could make on least squares, but I'm not going to make it. Okay. So a complex vector space is a space V where the vectors are composed of complex numbers. For example, here's a vector composed of complex numbers. As dimension 2, it's in C2 instead of R2, where C is your complex vector space, okay? And your scalars are complex numbers. Now, it should be clear that when you multiply a scalar, a complex number, might look like this, right? And it's clear that if I multiply this through, multiply this by this, and multiply this by this, I'm going to get a complex number. Might even be real, but not in this case. Okay. And what do you get here? I multiply this by this, I get 2 here, and I get 20 here, so I get 22. Now it's negative 20i squared, but that's 20, right? So this would be 22, and then what times I? Well, I get 5 times I and minus 8 times I, which is minus 3i. And you can verify that, or, you know, what's even more fun, find that I made a mistake and correct it. Okay. And 1 minus 4i times negative 3i is just negative 3i plus 12. Of course, we'd usually write that as 12 minus 3i, because usually we write the real part first. But the point is that this is just another vector in C2. And that 3 is really grotesque. There's a thing on the board there. Not doing a good job of it. Okay, anyhow, you get the idea. So it's really easy to prove this. Look at how your book proves it. You know, think, how would I write this out if I wanted to prove it in general? Okay, but it's very easy. And all the vector space axioms are easily shown to work. Okay. So you could have a linear transformation defined by a complex matrix, right? So complex matrix, for example, it might be 2 minus 3i, negative 5 plus 4i, 6 plus square root of 2i, okay, and negative 5/2 plus 3i. Any old 4 complex numbers would give you a 2x2 complex matrix, okay? And this could be then a transformation. Okay, this could define a transformation. Okay. So almost everything we've learned to do with real vector spaces works for complex vector spaces. The one thing, though, that's a little weird and, you know, not really hard to understand after you get my lucid explanation, is how about an inner product? Okay, we know inner product spaces are really important. you gotta be careful. Because whereas in real spaces, like a dot product of two vectors can't be negative. Or a dot product, sorry, dot product of a vector with itself can't be negative. Okay? Because, you know, if you dot AB with AB, you're going to get A squared plus B squared. That's always non-negative. Okay? I say it's always positive, but unless the vector is zero, it's always positive. And then we say that the dot product or any inner product has to be positive definite. And when you dot, or when you do an inner product of a vector with itself, you got to get a positive number unless the vector is zero, in which case you get zero. And that's positive definite. You got to be careful about positive definite property. Now, the main inner product we're going to deal with here, because we're not going to go deeply into complex vector spaces, is just your dot product. So I'm just going to do the dot product, okay? Okay. You can't say that AB dot AB is A squared plus B squared. I want to change my notation. I'm going to think that through. And I want to use AB differently. Not thinking that clearly. Talk about complex numbers, so we're going to use Z, Z1, Z2. Okay, well, let's just say that we're just going to consider, it's not even to consider that. Consider this. C squared would be A plus BI quantity squared, right? So that's A squared minus B squared, okay? Plus I times 2AB. Okay. This not only could be negative, It's not even real in most cases. So this wouldn't make any sense at all. Okay? Wouldn't make any sense at all as a dot product. And this is what gives a little twist to the matrix algebra and the properties of complex vector spaces when you get into inner products especially. Okay, so we defined this to be product of Z1, Z1 bar and Z2, Z2 bar, the complex conjugates. Okay. Now consider ZZ bar would then equal like A plus BI times A minus BI. Which is A squared plus B squared. Okay. So our inner product, and of course we need an inner product, or at least our dot product here, and other inner products, you got to do similar things like if it's the integral of F times G, it would actually be the integral of F times G bar. Okay. So define my notation's messed up again. I'll write these as vectors, feel that way. Define Z times W. Kind of like this, okay? Okay. Okay, I got to this point and everybody stood up to leave and I realized that I'd held everybody over about 8 minutes. So sorry, not totally with it this morning. But there we have it. And the homework will be posted.